This video explains how to use a relay to control high current devices with your Raspberry Pi. You should already be familiar with how to isolate a circuit using optocouplers, and be familiar with the function of diodes. You should be familiar with several different ways to make and break connections in an electrical circuit. The simplest, of course, is a mechanical switch, though it needs someone to be physically present to activate. The transistor solves this problem by using a small current to switch the transistor. Unfortunately, one limitation of the transistor is that the base is not electrically isolated from the circuit, which could potentially result in a damaged GPIO pin. The optocoupler deals with the problem of electrical isolation by using light to activate a photosensitive transistor. The main limitation of the photocoupler is that it can only pass small currents through its collector. The relay is another switching device. It also provides electrical isolation, but instead of using light for switching, it uses a coil to produce a strong magnetic field which can move an internal switch. As this mechanism is mechanical, it's prone to mechanical failure, but the relay's strength is that it can deal with much higher currents than typical transistors and especially optocouplers. We'll be looking at the SRD 5V SLC relay module. Its coil requires 5 volts at a current of approximately 60 milliamps. This is a considerable current, but we can safely provide this from the Raspberry Pi's 5V rail. It has two sets of ratings, a TUV and a UL rating. The UL rating is more conservative, but still well above what we'll be attempting in this video. The plastic casing is fairly easy to remove with a knife. Inside we see one of two pins that are connected to the coil. If we apply current to the coil, we see that the armature moves and makes contact with a second metal plate. In this case, the top plate is connected to the NC pin, and the bottom plate is connected to the NO pin. The relay is completely encased in plastic. If we flip it over, we see 5 connections. 2 of the pins connect to the magnetizing coil inside. It doesn't matter which end receives a positive voltage, as the polarity of the voltage simply affects the polarity of the magnetic field produced. A north pole and a south pole will equally pull on the metal switch inside. The remaining 3 pins are for the switch. This type of relay is known as a single pole double throw relay, or simply an SPDT relay. The pole refers to the center wire, which can either be thrown up to connect to the top pin or thrown down to connect to the bottom pin. This is the circuit diagram with the pins appropriately colored. COM stands for common, as it is always connected to the switch. NO and NC stand for normally open and normally closed. When we put together our circuit, we'll connect the component needing switching to the NO and COM pins, so that it's only powered when the relay is switched on. To start off our circuit, we'll use the transistor optocoupler pairing that we used before. If you're unsure how this circuit works, check out the optocoupler video first, as this circuit is discussed in detail. This circuit will provide electrical isolation from the relay module, though it won't be able to provide enough current to directly power the relay coil. We can solve this by using a transistor connected to the emitter of the optocoupler. The MPS 2222A has a max collector current of 600 milliamps, which is well above the 60 milliamps required for the relay coil. To activate the transistor, we need a voltage source and a connection to ground. I've used 5 volts, as this voltage source can also be used to power the relay's coil. Next, we need to attach the relay with a diode connected in parallel. I'll explain the role of the diode in a moment. Let's first go over how this circuit works. If the optocoupler is not active, no current can pass down this branch. At no point can current pass down this branch, as the diode only allows current to flow in the opposite direction. And current cannot proceed down this branch, as it cannot go through the transistor when no current is passing into the transistor's base. So with the optocoupler off, the relay remains switched to the NC pin. When the optocoupler is active, current can pass from 5 volts to ground through the base of the transistor. That makes the transistor conductive, which means current can pass through the coil and then to ground. Assuming a beta value of 75 for the transistor and recalling that we need 60 milliamps to pass through the coil, we can calculate the resistance of the base resistor to be about 5.1 kiloohms. We need to include the diode in this circuit to prevent having a voltage spike from the relay. This can occur when the coil is switched off, as energy is built up in the coil's magnetic field. The diode provides a path for the current to continue flowing through the coil until that stored energy is dissipated. This process takes roughly a millisecond, as the diode quickly dissipates the stored energy. All that's left to do now is connect a voltage source to the COM pin and the NO pin to ground, with the electrical component along either of the 2 wires. I've chosen a 10-watt LED, which at 9 volts will run at 600 milliamps, well above what the Raspberry Pi can provide on its own. Note that to take advantage of the opto-isolator, you should use a separate power supply for the 5 volts applied across the coil. In this circuit, I'm not using a separate voltage source for the relay coil. I did this mainly to show that the circuit could be powered from the Raspberry Pi if need be. Thus, we only need 3 pins from the Raspberry Pi, one to 5 volts, one to ground, and one to a GPIO pin. Of course, the high power LED still needs a separate power supply, as it requires a greater voltage and a much greater current. A 10-watt LED is actually incredibly bright and not something you can safely look at directly. The code is a simple loop which sets the GPIO pin high for half a second, and then low for half a second. Notice that each time the relay closes or opens, you can hear a click. Of course, you may want a simpler solution, such as a pre-assembled relay board. As the board uses the same relay modules as discussed earlier, we already know that the relay voltage JD-VCC is 5 volts and will require 60 milliamps. To control each relay, a GPIO pin must be connected to an input pin. The input pins are designed to work off of 5 volts, but should still work off of 3.3 volts, and they will draw about 2 milliamps of current from the connected GPIO pin. Lastly, the module's inputs are active low, which means that the relay is triggered when the GPIO pin is set to 0 volts. Let's first see if we can recognize any similarities between the relay circuit already discussed and this relay board. The board uses an optocoupler chip. There is a diode to prevent a voltage spike in the coil. It has an LED in series with the input pin to show when a current is present. The board uses 2 resistors, whereas our circuit used 3. And the board only uses 1 transistor, whereas our circuit had 2. So obviously a lot of similarities, but there exist some differences which we should go over. Looking at the circuit diagram for the relay board, we see that the right side remains the same, though with a weaker resistor on the transistor. On the left-hand side, things are greatly different. We see that instead of using a transistor to control the optocoupler, the GPIO pin is directly connected. This might seem odd, as the optocoupler's datasheet lists 20 milliamps as the normal operating current. Instead, this circuit has the optocoupler running at only 2 milliamps. Such a small current will only dimly light the LED in the optocoupler, and result in the photosensitive transistor being less conductive than when it receives more light. But this doesn't matter, as the weak signal will be amplified by another transistor. Now we must decide on the voltages for VCC and JD-VCC. As the relay requires 5 volts to reliably trigger, we need to set JD-VCC to 5 volts. VCC is a little different, and we have a few options. If we connect VCC to the 5 volt rail of the Raspberry Pi, everything will work fine when the GPIO pin is set low to 0 volts. On the other hand, when the pin is set high to 3.3 volts, there will be a potential difference of 1.7 volts across the circuit. Now this shouldn't be enough to result in the optocoupler activating, but it's not ideal to not be able to make the voltage across this circuit go to 0. Another choice is to attach VCC to the 3.3 volt rail on the Raspberry Pi. This solves the previous problem, as the GPIO pin works off 3.3 volt logic. Of course, this circuit was designed with 5 volts in mind, so 3.3 volts is a little low, but I found that the relay would still activate when VCC was set to as little as 3 volts. If you're daring, you could desolder the R1 resistor and replace it with a weaker one. I'm guessing a 510 ohm resistor would work well. For me, I'll avoid any soldering and go with VCC set at 3.3 volts. Now looking at the pins, we see 2 separate headers. Usually JD, VCC, and VCC will be connected by a jumper, which simply connects the 2 pins. As we plan to set JD, VCC, and VCC to different voltage levels, we need to remove this jumper. We will connect the following pins to the relay board. Note that on this relay board, the ground pins are connected, so we don't need to worry about connecting the ground pin on the right-hand side. At the very edge of the board, we can see the symbol for the relay's switch pins. The center pin is COM and the other 2 pins are NO and NC. The connection for the high power LED is fairly simple. We want the LED to only turn on when the relay is triggered, so one terminal must be connected to the NO pin. So here I have one relay setup. If you want to use both, simply attach a second GPIO pin to the input pin 2 on the relay board. Let's give it a try. And we get the same result as before. For this video, I used a 9 volt power adapter. It provided a sufficient current at a relatively low voltage. If you want to use a relay to control mains electricity, there's something important to remember. Mains electricity can kill you. In this video, I've tried to be thorough in my explanation of how to use a relay with the Raspberry Pi, but things get much more complicated with higher currents. For instance, inductive loads respond differently than resistive loads, and electrical arcing in the relay becomes a real problem. In general, I discourage trying out things described on a video that can kill you. I think such things are best learned in person from a capable electrician or electrical engineer. For this reason, I suggest sticking with power adapters as a power source to connect to your relay. You still need to exercise a healthy amount of caution when using a power adapter, but they are much safer to work with.